Okay, so let's do some examples from the previous theorem. Now, the first differential equation is given like this. How I would solve this problem is that I would make a list. So we know we have to check three conditions, right? So the first condition is to make sure that the coefficients and the right hand side functions are continuous on the interval. So here the interval is from -1 to infinity. So for first condition, let's make a list of all the coefficients. So the first coefficient is x plus 2, then we have 3, then we have -2, then we have 2x as the right hand side function. Now if you look at this, all these functions, they are continuous functions, right? They are just simple, nice functions. They are continuous everywhere, nothing mathematically undefined, right? So they are good. So they are continuous specifically on this interval. So first condition checked. Good. Let's go to the second condition. Second condition says leading coefficient should not be 0 inside the interval. What is the leading coefficient? X plus 2. When do you expect x plus 2 to be 0? Well, when x is equal to -2. So is -2 inside the interval? Now check that. Interval is starting from -infinity and goes to infinity. So it has skipped -2, right? So -2 is not inside the interval. So second condition is valid, satisfied, because x plus 2 is not 0 for x values in the given interval. Okay, so interval we talk about x values. Okay, all right. Third condition is initial x point should be inside the interval. Initial x point is 0, as you can see in the question, right? Is 0 inside -1 to infinity? Of course, right? So yes, third condition satisfied. So what does this mean? You are guaranteed to have a unique solution in the interval -1 to infinity for this initial value problem. Okay, great. So let's go to the second example. So we have this differential equation. Let's make a list. First condition, what are the coefficients? So x minus 3, 4x, 7, natural log x. Now you want to know whether they are continuous on this interval, right? Okay, let's see. X minus 3 is a nice simple function, continuous. 4x, again, no demons, continuous. 7, good, right? Constant. Natural log x. What do you think about natural log x? Is it a continuous function everywhere? No, right? Tell me, what is natural log 0? Natural log 0 is undefined. Okay, so you cannot take a log of a 0 or log of a negative number for a fact. So this natural log is not continuous when it's 0 or negative number. Now, do you have 0 and negative numbers, 0 or at least negative numbers in the interval? Yes, right. The interval is running from -infinity to 5. 0 is inside that interval, negative numbers are inside that interval. So natural log x is not well defined in this interval, not continuous in this interval. So the first condition is not satisfied. Okay, what do we have to do now? Do we have a unique solution? We don't even need to check other two conditions. So we don't know, right? We cannot guarantee a unique solution in this interval. Okay, if you want to guarantee, you have to use other theorem. So the theorem is not enough. So that is what we can conclude. Okay, or you can change the interval, you can change the initial condition appropriately and somehow find the interval where you can guarantee to have a unique solution. But that's a problem for the future. Okay, right. So the conditions did not satisfy, theorem is not sufficient. Okay, again, really understand, we cannot say that it does not have a unique solution. Okay, it's just I stated that we don't know, the theorem is not enough. Okay, let's go to the third example. Here let's make a list of coefficients. X square minus 16 to -7. The right hand side function is x plus 1. How about these four? Are they continuous? Yes, right? They are nice simple functions, right? Good. They are continuous everywhere, specifically from -infinity to 1. Okay, good. Let's go to the second condition. Leading coefficient is x square minus 16, and when is x square minus 16 0? Well, if x is equal to 4, right? Is that all? Don't forget negative 4. Negative 4 square is 16. 16 minus 16 is 0. So leading coefficient is 0 at these two values. Now, is these two values are inside the interval? Unfortunately, yes. Right? 4 is not inside the interval, but negative 4 is inside the interval. See? So, is the second condition satisfied? No, right? Second condition is violated because this leading coefficient is 0 inside the interval. Okay, so what can we say? Well, we stop there. We know that the theorem is not enough. So please use some other mathematics or change your interval or change your initial condition. It's just our theorem is not enough to guarantee a unique solution. But that does not mean you don't have a unique solution. It means it's just we don't know. Okay. All right. 4. Here in this example, let's list the coefficients. X plus 2, negative 7, 1, 2x. Again, these are nice simple functions. No mathematical demons. Well, good. So the first condition is satisfied because they are continuous functions. Leading coefficient is x plus 2. Coefficient of the highest derivative x plus 2. Where is it 0? Well, when x is equal to negative 2. Okay, good. So is negative 2 inside the interval? No, right? Interval is running from 1 to infinity. So you have skipped negative 2, right? So the leading coefficient is not 0 inside the interval. Good. So your second condition satisfied. Wow, good. Okay, let's go to the third condition. Fingers crossed. Third conditions said, remember what was the third condition? What was it? Well, initial point should be inside the interval. What is the initial point? 0. Is 0 inside the interval? No, right? Okay, this third condition is not satisfied. All right. So the third condition was not satisfied. So we don't know, right? We don't know whether we cannot guarantee a unique solution. Okay. But let's pause here now. Okay, again the theorem was not enough because the third condition was not satisfied. Now, if you want to find the interval for this particular initial value problem where you guarantee to have a unique solution, what can you do? Well, we can adjust the interval, right? So what was the problem with the interval? We didn't have 0, right? How about if I choose my interval to be negative 1 to infinity here? Well, now 0 is inside the interval, right? And the leading coefficient is still not 0 in this interval and still these are continuous. Okay, the same initial value problem is guaranteed to have a unique solution in this new interval. Let's say I had, not in that old interval, we don't know the old interval what happens, but in this interval, yes. So you can change your interval to get that guarantee. Okay, or you can change your initial condition even. Well, let's take our initial condition to be y2 is equal to something and y prime 2 is equal to something. Now 2 is inside this interval, right? That's another way also. Okay. All right. So let's do a final example and finish the video. Let's make a coefficient list 1, minus x square, negative 1 and 6. Look at them. They are the nicest functions, right? They are continuous everywhere. Most of them are constants. Excuse me. X square is a continuous function in this interval. So good. Second, leading coefficient. What is the leading coefficient? Leading coefficient is 1. 1 is never 0. So leading coefficient will be never 0. So automatically second condition also satisfied. Third condition. Wow, this is easy. What is the initial point? 0, right? Is 0 inside the interval? Of course, yes, right? So interval is running from negative infinity to infinity. So the third condition also satisfied. Then we are guaranteed to have a unique solution for this initial value problem in this interval. Okay, so that is those are some examples. Yeah, thank you.